threshold approach temperature. In many cases, the selected delta T minimum is such that no pitch exists. Means if we select delta T minimum is 5 and delta T minimum secondly is 10. So there is so many difference of this pitch point where it affects the पीच पॉइंट मीन्स अगर हम डेल्टा टी मिनिमम 5 सिलेक्ट करते हैं तो क्या हमें पीच पॉइंट मिलता है कि नहीं, वो हमें चेक करना पड़ेगा. by any of the method you can check this, by graphical method or by temperature interval method, composite curve method, you can check this, right? So MER design calls for either hot or cold UTD to be used, but not both. So the definition of the threshold approach temperature is that the critical delta T minimum below which no pitch exists. मीन्स ऐसा एक डेल्टा टी मिनिमम हमें मिल जाए कि उससे नीचे कोई पीच एग्जिस्ट नहीं करता. हाउ? if let's assume कि we are having a delta T minimum 5, then we will take 10, then we will take 20, 30, 40. We will get some of the answer of the QH minimum, hot utility and cold utility. But we will assume that कि threshold approach temperature उसका 80 डिग्री सेल्सियस है, तो उसके बाद कोई भी पीच एग्जिस्ट नहीं करता, राइट? So that is your critical delta T minimum, or that is known as the threshold approach temperature. In the simple language we can say the delta ऐसा minimum approach temperature जिस पे आपको कोई पीच पॉइंट नहीं मिलेगा. मैं कभी कभी हम ऐसा डेटा लेता है कि हमें कोई पीच पॉइंट नहीं मिलता. मीन्स एट द एंड ऑफ द हम जब कास्केड हीट फाइंड आउट करते हैं तो हम उसमें प्लस प्लस करते जाते हैं, तो वहाँ हीट प्लस करते हैं तो हमें माइनस, जो हम वहाँ पे -25 है तो उस पर +25 करते हैं तो हमें वो ज़ीरो मिलता है, और वो ज़ीरो को हम पिंच पॉइंट कहते हैं. तो वो पिंच पॉइंट हमें नहीं मिलता. ऐसा क्रिटिकल टेम्परेचर, उसको हम थ्रेशोल्ड अप्रोच टेम्परेचर कहेंगे, राइट? So this figure shows the effect of changing the requirement of the delta T minimum on the composite curve. For a typical process in which the total enthalpy demand of the cold stream, that is denoted as delta Hc, and the hot stream requirement is denoted as the delta H, capital H, right? So here's the figure shows the effect, three effects, 1, 2 and 3. Let's see what this labeling of this diagram want to say. So first, it is noted that when delta HH is very much greater than delta HC, that we can show in the label 1 diagram. So the selected value of the delta T minimum affects the minimum amounts of hot and cold utilities that are requirements. Means the distance, horizontal distance, we in the composite curve method में हमने देखा है कि जो हम मिनिमम दोनों कर्व के बीच में जो हॉरिजॉन्टल मिनिमम डिस्टेंस होता है वो हम एज अ हॉट यूटिलिटी एंड कोल्ड यूटिलिटी refer करते हैं, right? So here the horizontal distance is only this. Means if we are having this condition that is shown in the label 1 diagram, means delta HH is higher, then we can say that it is required the minimum amount of hot and cold utility, right? So these diagrams want to say that now at the end of the cooling, where these duties are just the enthalpy overhangs at the each and end of the diagram. Means QH minimum and QC minimum refers the hot utility, minimum hot utility requirements, means MER targets, your MER targets. Now next, what is next? Reduction of the value of delta T minimum. Means what is the effect of delta T minimum here? That's we want to actually note. That is if we will decrease the delta T minimum, so what will happen to this curve diagram, hot curve and cold curve? So it will transfer to the left side of the diagram, right? So this delta HH is here shifted to the left side, right? So let's see the first diagram that it is here, this much horizontal distance is there, but in the second diagram we have uh, shifted it delta t minimum is decreased, so this we will shift it to the left side. This diagram, this curve is shifted to the left side, means no hot utility is required because there is a no horizontal distance between these two curves. So the this refers to the no a hot utility is required with the required cold utility. Now reduced to the QC threshold, that is equals to delta HH minus delta HC. The required cooling duty is defined by the first law. That is first law of thermodynamics, right? It is noted that the value of delta T minimum that makes his come about is threshold temperature difference, that is delta T threshold. Means it is noted that the value of delta T minimum that makes it come about is the threshold approach temperature. So let's see the second label diagram, third label diagram is shown in the QT diagram. Label 3, any further shift of the hot composite curve to the left will of course not reduce the required amount of cold utility below the QC threshold. Means at the critical value, if we will decrease the delta T minimum, that doesn't mean वो हमें कोल्ड यूटिलिटी की जो रिक्वायरमेंट है वो कम मिलेगी. It will split the required cooling duty into the portion at the hot end. Means it will split this duty, means it is splitted into two duties, QC1 and QC2. So and a portion at the cold end, means at one portion is required at the hot end of the hot curve, and one portion is required at the cold portion at the cold end. Means the total amount of duty required is QC1 plus QC2, right? So this is the meaning of the three diagrams. What summary says, let's see that. In summary, as shown on the plot of the utility targets is a function of delta T minimum on the top left of the figure. For the case where delta HH that is greater than delta HC, only QC threshold cooling utility is required. For the value where the delta T minimum is less than delta T threshold, means in the, as we have seen in the first label diagram, that delta HH is always greater than delta HC, then it is greater than delta HC, so only the hot cold cooling utility is required. For the values of the delta T minimum in excess of the delta T threshold, the process pinch exists and external cooling duties of QC minimum is required, that is delta HH minus delta HC plus X, where X is the external heating duties. Means if delta H it is not shifted to the left side, then hot utility is also required here, right? So second topic is optimum approach temperature. Now we have seen the what is threshold approach temperature. So based on this, what is the optimum approach temperature? So there is two conditions where the minimum approach temperature is tends to 0 and one is minimum approach temperature is tends to infinity. The delta T minimum tends to 0. The true pitch is approached at which area for the heat transfer approaches infinity. Means if we have taken the delta T minimum up is 0, then heat transfer area will reach the infinity and the minimum utility requirements are reduced to the absolutely minimum. Means our MER targets is reached to its minimum value. And the opposite side, delta, if we will take the delta T minimum infinity, then heat transfer area approaches the 0 and the utility requirements are increased to its maximum value with no heat exchange between the hot and cold streams. Means if it is infinity, then there is a no heat exchange in between the streams, but we will require only the hot utilities and cold utilities. the variation in the heat transfer area and utility requirements with delta T minimum translate into the variation in capital and operating cost, that we will see in the next figure how it is affected to the capital cost and operating cost. As delta T minimum decreases, the cost of the utilities decreases linearly until the threshold temperature is reached, or when the threshold temperature is reached, cost of the utilities will not reduce. That we will see. Let's see this diagram, cost versus the delta T minimum. Here we can see the when delta T threshold is achieved, then utilities cost will not decrease, it will be stable at that time, and its capital cost is decreased with the delta T minimum increasing, right? So this is the trade-off between the capital and utilities cost as the function of the delta T minimum. So this is the main importance of the delta T minimum in our heat exchanger network synthesis. So these two topics gives us idea about this importance. Now furthermore, when delta T minimum is less than or equal to delta T, there is a no pitch that we have seen, and the trade-offs between the capital and utility costs as delta T minimum decrease become less straightforward. The first impression would suggest that since the cost of the utility is fixed, decreasing delta T minimum increase its capital cost, and in implying that optimal delta T minimum must lie on or above delta T threshold. Means optimum value of the delta T minimum, that is must lie on or above delta 3, means its critical value. In fact, the capital cost depends on the delta T LM. LM means its logarithmic value rather than its minimum approach temperature. Only a few of heat exchanger in network are actually designed at the delta T minimum design constraint. So the effect of cost of the number of units in a design may be more significant than that of the value of delta T minimum. Means in the practical purpose they have used the delta T LM rather than delta T minimum. Okay. So thank you so much for that. And reference, yes, I've used is Seader and Seader book. The title is Product and Process Design Principles, the second edition. Thank you so much for listening. Please like, share and subscribe this channel and Illimitable Chemical Engineering.